Hey, it's Mr. Shrum, and I am going to go over magnetic forces today in this physical science tutorial. By the end of this lesson, you will know how to apply the right-hand rule to determine the magnetic forces on single charges and current carrying wires. So you're going to learn all about that in the upcoming slides. And for the introduction, we're going to talk about Hans Christian Ørsted. He was a Danish chemist and physicist who discovered the link between electricity and magnetism. His dad was a pharmacist, and he became very interested in science as a child. He spent his career as a professor of medicine at the University of Copenhagen in Denmark, the country's oldest and largest university and research institution. Ersted shared his knowledge with his colleagues and community. He submitted articles to newspapers and magazines. He gave lectures to teach his community how science was relevant to their lives. And just months before his death in 1851, Denmark declared a national holiday in recognition of Ersted's contributions. And here's a photo of him there. He conducted many kinds of experiments and demonstrations in his classroom, but it was Alessandro Volta's invention of the galvanic battery that inspired Ørsted to research electricity. In the spring of 1820, he experimented with electric current in wires. If you remember from our past lesson, the needle on a compass naturally points to Earth's magnetic north if the compass is not near an electrically charged wire. Ørsted found that when he placed a compass near an electrically charged wire, the needle deflected at a right angle to the current. His experiments proved the connection between magnetism and electricity. Here's one more note about Ørsted. He contributed to the field of chemistry. Aluminum compounds were well known at the time, but he was the first to use electric current to extract light, useful aluminum metal from them. All right, so I said the right-hand rule. Technically, there are more than one right-hand rules. Ørsted's discovery of how electricity and magnetism are related was very important because it showed that electric current produces a magnetic field. When a stationary charge and a magnet are close together, they have no effect on each other. But when you set a compass next to a current-carrying wire, the compass needle will rotate until it's perpendicular to the wire. The needle's position shows that the force on the magnetic pole of the compass is at a right angle to the direction of the current flowing through the wire. In order to design electronic devices and mechanical systems with electromagnetic components, it's important to be able to predict the direction of the magnetic field lines around a current-carrying wire. It's also important to understand how those field lines will affect moving electrical charges. Let's look at two ways to predict field direction and forces on moving charged particles in a magnetic field. And these rules are called the right-hand rules. The right-hand rules show you how to use your, you guessed it, your right hand to predict the direction of a magnetic field. They also help you find the force exerted by the presence of a magnetic field and the velocity of a charged particle. The magnetic field lines around a current-carrying wire form circles. When a charge is placed in a magnetic field, it will experience a force if it's moving relative to the magnetic field and its velocity is not parallel to the direction of the magnetic field. For example, when you place a compass near a wire carrying current, the compass is influenced by the magnetic force field of the wire. its needle will line up with the force field perpendicular to the wire. So, if the wire on a table is pointing north, a compass placed nearby will point east or west, depending on its position with respect to the wire and the direction of the current. The direction of these magnetic field lines is important to know and can be understood using the right-hand rules. Now look at each rule and how to use it to determine the direction of a magnetic field or force. And here's a diagram and the thumb and hand diagram here. All right, so the first right-hand rule, sometimes called the curl rule, because your fingers are curling around the wire. This will determine the direction of flow of the magnetic field lines with respect to the direction of an electric current. Imagine you are holding a wire in your right hand with your fingers curled around it, as if you were holding a microphone. If you keep your thumb pointed in the direction of the current, which is the I, the direction of your fingers' curl predicts the direction of the magnetic field, B. So we have I for current and B for the magnetic field. You can also apply the first right-hand rule to a current-carrying loop of wire or to a coil of wire, also called a solenoid, and we'll look at that later. The direction of the magnetic field produced by each wire loop in a solenoid is the same. So the fields add together to create a stronger magnetic field. The larger the number of loops in the coil, the greater the strength of the magnetic field. Here's the second right-hand rule. This is known as the palm rule, because instead of curling your fingers, you're going to lie your hand flat. And this can help you figure out the direction of the force on a current as a result of the magnetic field through which it travels. So the other one told you the direction of the magnetic field. This one will give you the direction of the force on a current. So using your right hand, you're going to point your fingers in the direction of the magnetic field, B. Point your thumb in the direction of the current, I. And the palm of your hand will show the direction of the force exerted by the magnetic field on the moving charges in the wire. This rule is useful anytime you want to understand how a magnetic field interacts with a current or a moving charge of any kind, such as a stream of electrons. For example, this rule is helpful in understanding the forces acting on a loop of wire in a motor or a generator. With a constant magnetic field and current running in opposite directions on the two sides of the loop will be forced to rotate. Remember, these deal with the perpendicular nature of the current carrying wire and the direction of the force exerted by the magnetic field. Everything's perpendicular when it comes to electromagnetism. Okay, and then next time, I'll get into this lesson activity, and that will help you understand the right-hand rule. But until next time, have a great rest of your day, and I will see you all later. Bye-bye.